This video will cover parts of Chapter 6. Chapter 6 is about the network layer. Some of the things that we'll talk about are routers, routing, configuring a Cisco router, and network layer protocols. You can see here that the network layer is third from the bottom and deals with packets. At the network layer, we encapsulate our frames and add IP address information so we can correctly deliver the packets to the correct hosts. The network layer is in charge of our end-to-end transport processes. This involves addressing end devices, our encapsulation by adding those IP addresses to the frames, routing by taking a look at the destination IP address, and the de-encapsulation where we strip off the IP address at the receiving end, take a look at the frame, verify our MAC addresses, and continue to send to the other layers. Some common protocols that work at the network layer are IP version 4 and IP version 6. The main topic of this class will be IPv4, but we'll talk a little bit about IPv6 as well. Some legacy protocols that work at the network layer is IPX, which is part of the IPX SPX protocol suite, AppleTalk, and the connectionless network service. We will not get into these protocols in this class. IP is very similar to UDP in the fact that IP is connectionless. There is no connection established before we send our data packets. There's no three-way handshake. It's considered best effort. Essentially, IP says, I'm going to send this packet. I don't care if it makes it there or not. It's my best effort. I'm just going to go ahead and send it. Hope it gets there. It is media independent, which means it can operate independently of the media carrying the data. So it doesn't care if it's fiber optic, wireless, or over copper. It will go ahead and send the data and hope that it gets there. They relate IP to the mail system. When you send a letter to somebody, you don't know if the person's going to be home the day it's delivered. That person doesn't know if the letter has arrived, and we don't really know if the receiver can even read that letter. Maybe they can't read our handwriting, or maybe they don't speak the language that we wrote the letter in. Very similar to IP. With IP, again, it's a best effort delivery. We just go ahead and we send it. We don't know if the computer or the receiving device is up and running. We don't know if they have that protocol installed. We don't know, or the receiving device doesn't know when that packet is coming. Because IP is unreliable in a best effort protocol, we cannot guarantee that all packets will be sent. We must rely on other protocols and other delivery methods to make sure that our packets get to where we need to go. So up at the transport layer, we had our segment, and into the segment we add our IP header, and then when we pass it down to the data link layer, we will then add the data link layer header, which would include the MAC addresses. So again, we're working with what are known as packets here at the network layer. This is what a IP version 4 packet header would look like. There's all these different fields that are in here: time to live, version, protocol, header checksum. The main ones that I want you to know about are the version, time to live, and mainly the source IP address and destination IP address. If you were to use the Wireshark application and sniff some packets on the network, you could take a look at this IP version 4 header. Again, some of the things that we would see that are in there are the version, we see the header length, we see our source and destination IP addresses, which are probably the most important to us. We see a header checksum and some other things, but again, the main things I want you to know about are the version that we're working with IPv4 here, and that we have the source and destination IP addresses. You may have heard that IP version 4 is going to expire or is running out. It's not necessarily going to expire, but we do have a depletion of the IPv4 addresses that are available to give out. IP version 4 also expands our routing table rapidly, and it lacks end-to-end connectivity. Typically, we're going through some type of NAT or network address translation to get from one point to the next. To address some of these problems, they developed a protocol known as IPv6 or IP version 6. With this, we have an increased address space. With IP version 4, we only had about 4 billion IP addresses. Well, with IP version 6, we have 340 undecillion addresses, or 340 trillion, as some people like to say. This should be more than enough addresses to last us a lifetime. It does eliminate the need for NAT, and does offer some integrated security with IPsec. We'll talk a little bv6 more about IPv6 in detail in Chapter 9. This slide here compares an IP version 4 header to an IP version 6 header. Some people may tell you that the IP version 6 header has gotten a lot larger. That is true in terms of size, but they've actually simplified it. The reason why it's larger in terms of size is because our IP addresses are a lot bigger with IP version 6 compared to IP version 4. But we can see here that it does not contain as much information. The main things I would like you to know about with the IP version 6 header is the source IP address and destination IP address, and then also the version. Here is an IP version 6 header that's been sniffed on the network through Wireshark. We can see here that the version is 6. Here we can see what an IP version 6 address looks like. Notice it's in hexadecimal and it's 128 bits long compared to the 32 bits in length of an IP version 4 header. At the network layer, we're in charge of routing, getting our packets from one destination to the next. The first thing that your PC must do to deliver a packet is decide where to send it next. And the first thing that it will do is look at its own routing table. You can go to your command prompt and issue a route print, and you can see all of the destination networks that your computer knows about. Some of these destinations are directly on its own network or its LAN, and some of these are on foreign networks. And if they're on a foreign network, we would then forward to the default gateway. So a default gateway is a way outside of our network, and a default gateway is always going to be a router. The default gateway address is always going to be, or I should say typically is going to be, the closest interface of the closest router, which is usually a fast Ethernet or gigabit Ethernet. So in this scenario here, the default gateway address for PC1 and for PC2 is the 192.168.10.1 address. So if these computers want to communicate outside of their local area network, they would have to have the default gateway setting present, and that setting would be this router, and they would send any packets for remote networks to that address. If that default gateway setting was not present, the PCs still could communicate with each other through this switch just fine, but they could not communicate outside of their LAN. One thing I'd like to point out here in the host routing table is the destination network of 0.0.0.0 with the subnet mask of 0000. This is in here to meet any network that we do not have a route for. So if this PC were to get a packet destined for the 192.168.10.5 address, the 192.168.10.5 address would meet or reach this network in here, the 10 network. I said 10.5, so it's on the 10.0 network. The gateway is on the link, meaning it's a local area network PC. And we would use our local interface to go ahead and send it to that address. If this PC wanted to send a packet to the 15.4.3 network, there is no route in here for the 15.4.3 network, but there is this gateway of last resort in here. It would meet this criteria. Any network that I do not have meets the quad zeros. And what we would do is we would send it to our gateway address now of 10.1 out of our local interface, get it to our default gateway, and hopefully our default gateway can deliver it or at least get it to the next router. This is an example of an IP version 6 host routing table, very similar except we're working with IP version 6 addresses. When we send a packet to our default gateway or the router must then make a forwarding decision. Routers can only make forwarding decisions based upon networks that they have in their routing table. In order to view a routing table on a Cisco router, we issue the show IP route command. All of our directly connected networks, as in this example here, will show up automatically for us when we configure and turn on our interfaces. So this R1 router would have the 192.168.10.0, the 11.0, and the 209.165.200.224 networks inside of its routing table, and those will be put in automatically for us. They can route traffic to anything that is directly connected to them. Other networks, such as remote networks, need to either be put in there manually with a static route, or they need to be learned through a dynamic routing protocol such as EIGRP, RIP, or OSPF. You'll get into how to enter in these routes in the next Cisco class. The next two slides here give us a breakdown of how a routing table entry looks inside of a Cisco router. This is a directly connected route here for R1. We have the A section here, which identifies how the network was learned. We have the B section, which identifies the destination network or the networks that we can get to. And the C is the interface that we send out. So let's take a look at one of these. The first one, the C network, means it's directly connected, and it's the 192.168.10.0 network. It says we get to that out of our gigabit Ethernet 00. Let's see if that makes sense. So R1 can get the 10.0 network, that's this network up here, upper left, out of its gigabit Ethernet 00. Makes sense to me. A remote network statement is very similar. It has a few more fields, but the general nature of it is very similar to our directly connected. And again, we'll get into more detail with this in the next Cisco class. We'll take a look at this one here. For R1, the 10.110 network can be gotten to by sending to the 209.165.200.226 address out of its serial 000. So let's see if that makes sense. So here's R1. It says we can get the 10.110 network, which is over here, upper right. We can get to this network by sending to the address of 209.165.200.226. So that's this address right here. So what we're saying is to get to that network, send over to router 2 out of our serial 000, and then once router 2 gets it, router 2 would be able to deliver it for us because it is directly connected to us. The administrative distance and the metric determine the trustworthiness of our route source and the metric or the distance to get to that network. I have another video posted that gets into the different parts of the router. But this slide here shows some initial configurations of a router. There are a few different modes that we work with in the router. The first mode that we see is when we have a router and greater than sign. This is known as user exec mode, which doesn't give us a whole lot of capability. When we type enable, our prompt changes to router and pound. This is known as privilege mode. In privilege mode, we can do a lot of our show commands and get an idea of what's going on with the router. With router, if we want to make any changes to the router that would affect it globally, we get into configure terminal, or known as global configuration mode. This would be a great slide to reference when you have to do some of the basic configurations, such as passwords, encrypting your passwords, host names, a banner message of the day, and copying your startup configuration. This slide here shows us how we can configure interfaces with a Cisco router. One thing I'd like to note here is that with the Cisco IOS, you can pretty much shorten every command. Notice here where they have interface gigabit Ethernet 00, you can shorten that with just int G or int GI. You can also shorten IP address with IP add. Instead of no shutdown, they do a no shut. Another thing you can do is as you're starting to type the command, you can hit your tab key, and the tab key will attempt to finish off the command that you are typing. After you configure any interface, you should verify that it's up and running. One command you can use is the show IP interface brief. This will show you your interfaces that your router has, the IP addresses, and whether or not they're up and running. If they're listed as administratively down or down, that means that they have not been configured or turned on. We talked about our hosts or our PCs having default gateways. If you configure a switch to be administered remotely, you will also need to configure the default gateway on a switch. To configure the default gateway on the switch, you use the IP default-gateway command with the IP address of the nearest router. In order for this to work, we would have to have a VLAN set up, and with that VLAN interface set up, we can now configure that switch remotely. Quick summary here for the network layer. Remember that the network layer is responsible for IP addressing, encapsulation with their IP addresses, routing, and de-encapsulation. Our main protocol that we talk about in this chapter is IP version 4, which the internet is largely based off of. We've also started to move towards IP version 6 to take advantage of several different things, such as a larger address space. We talked about routing tables for our hosts and also for our routers. We talked about the default gateway that must be used on our hosts and switches if we want to get outside of our local network. We talked a little bit about how the routing table looks with a host and how a routing table looks with a router. And lastly, we showed some of the basic configurations that you can perform on the router and their respective commands. That is all for this video on the network layer. Thanks for watching.